Good morning, everybody. Thank you for joining us on this webinar on Introduction to UDFBs. It's about a 20-minute presentation, and then if there's any questions, we can get into those at the end.
Hello and welcome to today's webinar. Today we're going to be looking at an introduction to user-defined function blocks. Let's get started. Let's look at our agenda for today. We'll look at how to create user-defined function blocks and how to use them in your program. We'll also look at fixing mistakes in your code so you don't replicate things that might not work. We'll look at an example of nesting UDFBs and talk about the features of Cscape for these UDFBs. There will be demonstrations throughout, and we'll finish with a Q&A session. Let's start by looking at what user-defined function blocks are. As the name suggests, these are function blocks made by users, offering an efficient way to make reusable code. They are supported in two Cscape logic styles: advanced ladder with tags, supporting user-defined function blocks. Additionally, we offer the IEC 61131 language set, which has supported user-defined function blocks for quite some time. The logic within a function block consists of standard instructions, whether Boolean or other function blocks, including user-defined function blocks. One key feature of UDFBs is the ability to use multiple instances scattered throughout your code. So how does a UDFB compare to a subroutine? Subroutines are called using the call instruction, and you can use multiple call instructions in your code. However, no matter how many times you call a subroutine, it's the same code with the same variables. On the other hand, user-defined function blocks can be placed directly in the main logic blocks throughout your program, offering multiple instances. Unlike subroutines, which only have a single instance with the same set of variables each time you call, UDFBs have a unique set of variables for each instance. This is a significant difference between the two. Both are essential tools for maintaining well-organized and code. Now we'll look at the process for using UDFBs. First, create the function block. Use an instance of it in your logic, debug it to ensure it's free of bugs. You want to confirm its reliability before replicating it. Once proven, proliferate the code by adding additional instances in the same project or saving it for future projects. Creating a UDFB involves naming it, assigning input variables, internal or private variables, adding output variables, and defining the logic. If you discover the need for more variables while creating the logic, it's an iterative process you can perform. Now we'll look at our example today. We'll create a user-defined function block to calculate the volume of liquid in a vertically oriented cylindrical tank. While there are more efficient methods for this calculation, our goal is to provide a straightforward example of using user-defined function blocks. For this function block, our input variables will be the tank diameter in meters or feet and the fill height of the liquid in meters or feet. It's a simple function block without internal variables, and the output variable is the volume of liquid in cubic units. To accomplish this, our function block needs to take into account the formula that volume equals pi times the radius of the tank squared times the height of the liquid. Now we'll look at how we create this user-defined function block. So now we're in Cscape, and we're going to look at how we're going to define this particular liquid volume user-defined function block. Before you start, make sure you have tag-based advanced logic selected when creating a program. To begin, go to the top left of your screen to UDFB modules, right-click and select a new enhanced logic block and give it the name lic_vol, short for liquid volume, which is how we're going to reference it for the rest of this tutorial. Now with the UDFB created, we can see this screen, which looks very similar to a subroutine, but remember, they're not the same. So as you can see, when we created the new UDFB lick underscore vol, a new window was created for the project variable window. Under retained variables, we start by setting our variables to liquid volume. And we do this by right-clicking, scrolling up, and selecting Add Variable. We are then prompted between selecting an input parameter, an output parameter, and a private variable. So now we'll enter our input and output variables. First, we'll enter our input parameter diameter real, our input parameter fill level as type real, and lastly, our output parameter volume as type real. So now we're going to code. We'll begin by placing down a normally open contact here. Now we'll place a standard and all tag into our contract. What we would usually do is place an always on variable that's tagged as 7. But in this case, we already have an array that's been created called S that's tagged to all system bits. Therefore, S sub 6 is equivalent to always on because arrays are always 0 based, making S sub 6 equivalent to %S7. So now we're going to add a 6 here. Next, we're going to add a math expression. So to do this, we go to the top left of our screen, Math Operations, take an expression and place it here along with the top row. So now we'll begin to write our equation. So to reiterate, the volume of water is calculated by multiplying the radius squared by pi by the height of the fill level. We're working with real variables, so we're going to adjust the settings as such by clicking here, scrolling down and selecting real. To start, we have to place our volume variable. And to do this, we can't just write volume, but we have to call lick underscore vol to gain access to it. So we write lick underscore vol dot volume equals. So now we want to get the radius, but we don't have it. We do have the diameter. So open bracket, lick underscore vol dot diameter, and we're going to divide that by 2 to find the radius, and close bracket. So before we square it, we're going to add in at the beginning. So 3.14159 and multiply that by the radius. To square the radius, we're just going to multiply it by itself. So open bracket, lick underscore vol dot diameter divided by 2. Close bracket again. And now the last variable to add is fill level. So we're going to add that to the end. So multiplied by lick underscore vol dot fill level. So now everything seems fine and we're going to click OK. So that's popped up and everything is fine. So here we've created a base UDFB which takes the diameter and fill level of a tank and gives back as volume. So for example, if the input are in inches, the output would be in cubic inches. If the input is in meters, the output would be in cubic meters. Once we've created the logic of our UDFB, the next step is creating a unique instance of that function block and to place it somewhere in our logic. So we'll look at that now. Before we start using our newly defined function, let's assume that this application, the reason we created a UDFB, was to quickly calculate the volume of water in multiple tanks. So to make this example more realistic, we're going to create an array of tanks. We're going to utilize the structure feature so that we can have a series of variables in a structure format, all tied to the array of tanks. So we'll start by creating a structure. To do so, we go to Retain Variables, right-click, scroll up, and select Add Structure. So now that it's created, we're going to rename it. So we right-click, scroll up, and select Name Structure, and we're going to call it Tank. So now we'll add some variables to our structure. So we'll add diameter, fill level, and volume. These variables are not required to have the same names as in the UDFB, but we're naming them such for clarity. So now we just add our last variables, fill level and volume. We also have to make sure that they're all type real. So let's do that. Just to demonstrate variables within the tank don't have to be used, we're going to create a new variable height, which displays the height of the tank itself with type real. So now we're going to create a variable that utilizes the structure tank. Right, scroll up and select add variable, which we're going to rename to water tank. Then double click, scroll down the list and select tank. So now in this example, we're going to say we have 16 water tanks. And to show this, we're going to dimension water tank to 16. So now we have water tank 0 to water tank 15, which all follow the structure with diameter, fill level, volume, and height. Now we're going to utilize a UDFB to calculate the volume for some of these water tanks. So in the main area, in the logic, and we have an always on tag S6 data on the top row. If you look under project toolbox, we have a category called UDFB, and if we expand that, we can see the liquid volume UDFB that we created. So now we're going to select that UDFB and place it on the top row. One of the unique powers of UDFBs is the ability to have multiple instances of the same UDFB. So now we have to name this instance, and we're going to call it water underscore tank 1. So now that we've created an instance water tank 1, we see that we have a pop-up that is all of our predefined input and output specifications. To start, we just have to select our diameter. And we do this by clicking our arrow here to pull up a list of our variables. So we now see our water tank array, and if we click it into play, it displays each item in the array. So now we're going to select the diameter and water tank sub 0. We can now repeat this process to the other variables water tank sub 0. We're doing the same for fill level and volume. Now that we've created the calculation for the volume of water tank and water tank sub 0, we can repeat the process for the rest of the water tanks. So we're going to drop the normally open contact name and S6 for always on, and next we're going to drop the liquid volume UDFB, and we have to give it a new instance name, which we're going to do and call it water tank 2. So now we're going to fill in the parameters. So for diameter, water tank sub 1 diameter, and fill level, water tank sub 1 fill level, and volume, water tank sub 1 volume. So that's how you utilize multiple instances of this simple UDFB. The last thing you want to do is to not test your function blocks and have bugs throughout your code. So we'll look at debugging your UDFB now. When we debug, we only want a single instance to be enabled. This allows us to really debug the internal of the function block with only one instance calling it, which makes troubleshooting much easier. So here we'll look at debugging UDFBs. It's very important that when you debug the UDFB itself, you only have one instance of the function block actually running. So what we've done here is we've temporarily changed this always on contact to a normally closed to prevent this second instance of the UDFB from executing. So now the only instance that's executing is this first function block here. So to debug, we're going to move over from the main module down to the UDFB module. And here's the logic. To debug today, we're going to use the data watt feature. So here we've already added the tank diameter for the first water tank, the fill level, and the UDFB is calculating the tank volume. So we'll double check the calculation here. so that looks good. Let's change the fill level from 2.5 to 2, and we'll look at the calculation again, and everything looks good. So we have successfully debugged our UDFB with only one instance of it actually running. So we can now go back to our main loop and effectively add as many instances as we need, have the UDFB, and be confident that it's working properly. Now we'll look at some additional capabilities in the UDFB implementation in Cscape. You can cascade UDFBs, meaning the output of one function block becomes the input to the next. However, remember the rule, one UDFB per row. Drawing it across rows won't work, but placing them on two consecutive rungs is perfectly fine. So if you're interested in cascading UDFBs, you have that capability. You can also safeguard your function blocks with OEM protection. OEM protection is a feature in Cscape for system integrators or OEMs who want users to utilize Cscape for debugging or making simple logic changes without revealing their intellectual property. This feature allows you to show the presence of logic in your main loop without revealing its contents. With UDFBs, you can provide function blocks to users for their programs with inputs and outputs, while keeping the internal logic hidden. To enable this feature, you need to activate security and OEM ladder support. Once enabled, you can right-click on the specific user-defined function block you want to protect in your program and select OEM Protect. Exporting and importing user-defined function blocks is handy for building library across projects. To export a coded and tested UDFB, right-click on the function block in the navigator, select Export, name the file, and store it. Later, in another project or for sharing, import it by right-clicking in the Logic Modules section, selecting Import, and retrieving this file. Currently, Cscape lacks a formal UDFB library function, but using export/import can help maintain your own library. We're also working on adding graphics elements to the UDFBs, allowing you to associate user interface objects like buttons and indicators with UDFB variables. This feature isn't available yet, but it's in development. You can also nest UDFBs, meaning you can create a function block that embeds another function block within its own logic. Look at an example of a nested UDFB now. So here we're taking a quick look at two UDFBs. The one on screen at the moment is called volume to gallons, which has two inputs and two outputs. One input is the cubic volume that was previously calculated, which can either be in cubic meters or cubic feet. The other input shows the volume coming in is metric or imperial. So if the Boolean value is 1, the volume is in cubic meters, and if it's 0, the volume is in cubic feet. Next, it's going to calculate two outputs, volume in number of gallons and number of litres. So if the input is imperial, it's going to convert from cubic feet to gallons and litres, and if the input is metric, it's going to convert from cubic meters to gallons and litres. So now we're going to look at the other UDFB we created called cylinder volume. This function takes linear dimensions of the tank along with the fill level of liquid, and it calculates the volume of liquid in cubic meters or cubic feet. It would also be used to find the volume in gallons and litres, and to do this we've embedded our previous UDFB inside it. This is displaying our nest capability, and to be sure that it works, we have to be certain that our inputs and outputs from this embedded function are passed through. To do this, we're going to take a look at the details of our embedded function, cylinder volume, and verify that the metric flag and volume total is passed through, and that there's a path for gallons and litres to pass outward. So if we look at our cylinder volume function, we can see that our metric flag and volume total have been passed through, and that there's a path for gallons and litres to pass out. So that's how you nest one UDFB inside another. That concludes our webinar for today. Thank you so much for listening, and the Q&A session will begin shortly.
Okay, there's nothing in as yet. This is the last webinar before the Christmas break. We will be putting up a new list in January of what's coming. But for now, this is the last one for the year. Okay, I'm just giving a little bit of time there for questions, but I don't see anything coming in. Thanks all for joining, and we'll hope to see you back on the webinars in January when we resume again.